Hello everyone. Welcome to Orgo 2 Lab Prelab lecture for electrophilic aromatic substitution. A lot of times I just say EAS for short, so do be prepared for that, as is also shown in the lab report in the manual. All right, so for electrophilic aromatic substitution, as the name would suggest, aromatic, we are going to be seeing a lot of benzene and benzene derivatives. So you can tell here, phenol, toluene, uh, acetanilide, one naphthol, anisole, diphenyl ether, bromophenol, right? So, and specifically the electrophilic aromatic substitution we're going to be looking at is brominating. So we're going to be trying to replace a hydrogen on the benzene ring with a bromine. And so so just generically, kind of what we're seeing here, our simplest case, if we just started with benzene without anything already on it, if we started with the benzene, we're going to be seeing some type of electrophile that's going to be substituted. So the hydrogen and the electrophile will change. And so we have these five general electrophilic aromatic substitution reactions we can have, where we can halogenate using either bromine or chlorine. And so what we see here, X2 would be either Cl2 or Br2, and then we would have a catalyst here, like iron chloride, iron bromide. And in the chlorine case, you can even have another catalyst, aluminum chloride. But then there are these others as well, where you can do a nitration, where you're substituting a nitro group onto the ring, or you can have sulfonation, where you have your SO3H, and then you can do Friedel-Crafts alkylation and Friedel-Crafts acylation. And then these two I'm not really going to talk very much about because your next experiment actually focuses on Friedel-Crafts acylation. But you can see here yet again they are using a catalyst. Now, in terms of, we see generically we have to have an electrophile. So in this case, Br2, as it's written on the top of this arrow, or X2 as the way it's written on top of this arrow, is not in its electrophilic form, and that's why we have to have this catalyst. So kind of seeing what happens here when we turn this into an electrophile, as we generate an electrophile to react with our benzene, right? So if I had my benzene ring over here, all right, so Br2 and something like iron bromide, we would see first these two would react with each other, where we're going to see a lone pair from bromine attack the metal center of our iron bromide. And you can see that we make this weird adduct, this Lewis acid base adduct, where now the iron, a metal, has a negative charge and our bromine has a positive charge. So you can see here, right, we know electrophiles, right? We typically just symbolize them as E plus, right? Our electrophile is based off the fact that we have a positive bromine. Now, in the reaction, our benzene ring isn't actually going to attack that bromine, it's going to attack this one, all right? And we'll see that in a second in the mechanism. But the same thing is held true like if we're doing chlorination with Cl2, the lone pair of the chlorine in this case would attack our aluminum metal. And then we would see yet again, we have increased our metal halogen bond number by 1. We have a positive chlorine, a negative metal. Okay. Now this iron bromide and this aluminum chloride here, these are catalysts, so they would have to be regenerated to be considered catalysts, right? They get used, but they will be regenerated. Okay. And so once we create our electrophile here, we can see that our benzene here is going to act like a nucleophile, right? It's going to attack because the pi electrons are attacking, so it's going to act like a nucleophile. It's going to attack this neutral bromine so that we can break this bromine-bromine bond here and kind of satisfy that positive charge on the bromine, right? Like we see down here. Okay. Now, what winds up happening, we have broken aromaticity, and you should have learned at this point in the lecture that having an aromatic compound makes it very, very stable. And so you've broken aromaticity. So it's not as stable as it once was. Now, it still does have some stability due to the fact that there are resonance structures that you can have here. All right. Now, when you see something like this, this once was aromatic, but now a carbocation like this is called an arenium ion. All right, and it is resonance stabilized, but it's not as stable as if it were still aromatic. Now, as we said, the iron bromide here was a catalyst, so it's going to have to be regenerated. So we have an extra bromine there, and so that's why we see this iron bromine bond is going to break in favor of the bromine to attack a hydrogen here, and then we can break this carbon hydrogen bond here to give us back our aromatic compound, and we're even more stable. And so you can see here we did regenerate our catalyst there at the bottom, and as a byproduct we have HBr also as a byproduct. All right. Now, with that, we won't be doing things just as simple as starting with benzene. We're actually going to see benzene with different functional groups on it already. So you can see benzene with an alcohol group, an ether group. Here you have an ester, a phenol, a benzene ring already attached to it. You could have it with another chlorine, another bromine, something like that, or any of these, like a nitro, a carboxylic acid, an aldehyde, or a ketone. Functional group already added. Now, with that being said, all of these groups do tend to act different. And what we see here is in these we have what are considered both electron donating groups and electron withdrawing groups. Electron donating groups are very easy to recognize because you're looking for something with lone pairs. So you see here the example they give you is like OMe or NH2. So when you go and you look at benzene ring with one of those functional groups on it, why are they considered donating groups? So if we look here, right? That oxygen has 2 lone pair on it. And so we consider it a donating group because if you look at the lone pair here, they can donate down into the ring, and then you can get another resonance structure here. Right, you're going to have a positive charge on the oxygen. We didn't mess with these 2 pi bonds, but see this one now moved out to that corner, so it gets an extra lone pair and it's negatively charged. So these donating groups will actually increase the nucleophilicity of our benzene ring because now the benzene ring was neutral and it was going to have to act like a nucleophile. But see, now this is an even better nucleophile because it's a negatively charged. It's no longer neutral, it's negatively charged. So if you can make that, we did sort of break the aromaticity in the way that you're used to seeing it, but we still have 2, 4, 6 pi electrons within that ring, so it's still aromatic. Okay, but this is going to be an even stronger nucleophile now, thanks to those electron donating, thanks to this electron donating group. And that's why you want to pay attention to all of these different ones we have that are electron donating here. And these electron donating groups are actually what we call activating substituents. So that's going back to this right here. Why is it activating? Because look, it actually made the benzene ring have a negative charge in it. So it's activating. It's an even stronger nucleophile to do its job in an electrophilic aromatic substitution reaction. Then these electron withdrawing groups do the exact opposite. You see where they deactivate the ring, and you're going to see resonance structures where the ring now has a positive charge circulating within it. Okay, now when we say this activating and deactivating, another way you could think about that is how fast also, these activating and deactivating groups can affect the rate at which our reaction occurs. So if I were to ask you something as simple, so if you just look, let's say we look at alcohol here versus this aldehyde group here. So really what am I doing here? I'm going to be comparing if I have phenol versus benzaldehyde here. If both of them, right, if I had a mixture of these and I said, all right, I'm going to do Br2 with the iron bromide now. If I'm going to have a mixture of these two and try and brominate, which one do you think is going to get brominated more readily? Well, it's going to be this one, right? This one's going to react the fastest because this has a lone pair that can donate into the ring and make the ring negatively charged. While this one does the exact opposite. Because you have this carbonyl here, it's actually going to try and pull that pi bond up to the oxygen and actually pull electron density out of the ring. So this has an activating group, this has a deactivating group, and so this one is going to readily react. Okay. Now, we know that, okay, since this is activating, this one's going to readily, this one will react the fastest upon this bromination. But also we have to recognize where it will go, because there are 1, 2, 3, 4, 5 other carbons in this benzene ring that it could go to. So where is it going to prefer to go? Well, if you pay attention to your donating groups, they tend to always put a negative charge at these 1, 2, 3 locations with respect to the original group. Okay, so what we call these are ortho. These top corners right here, these are ortho, and this bottom one here is para. All right, and so technically, if you just think about it like this, if you have a benzene ring and you've got your group on there, all right, if you look, that's where the group is connected. So if you take one step to the left or to the right, those are both ortho. Those are O's, ortho. If you take an additional step, those are both meta. And if you take your final step, that is para. So OMP. All right. You down with OMP? Yeah, you know me. All right. So what we're going to see here is when we have an activating group like this, like OH, it's going to put a negative charge on the ortho and the para positions. So when we brominate, that's where we're going to favor. Okay, now one thing to also consider here, right, and we see that, let me swap back over for a second, we see that here in those resonance structures. All right, we haven't actually even done the reaction yet, we're just seeing that overall our hybrid resonance form shows these partial negative charges at the ortho and para positions. Okay, now, that's before anything's ever happened. Okay, now the other thing is to recognize these ortho and para positions, one tends to be favored over the other, and it's para. Para tends to be favored over the ortho positions just because sometimes this group right here, this X group, can be very bulky. And so if it's bulky, it's going to be harder for say, bromine for it to be able to come in as efficiently. And so your para group does tend to be favored due to this lack of steric hindrance. Okay. And so that's also another reason why if you were to look at, say, a di-substituted benzene, you had two groups in it. And let's say the combination of both of them would say, oh, okay, they're both going to direct to that carbon position. But odds are you're not going to see, so let's say for Br2 with FeBr3, right? That bromine, you're not going to get a bromine on that carbon because these two are going to be bulky enough, sterically enough, that bromine's not going to be able to go there. So it's going to have to go to one of these other three positions. All right, it's almost a guarantee that anytime you have a di-substituted anything, a di-substituted benzene ring, nothing's going to go there, right? There may be an exception to that rule, but as a good rule of thumb, you can always pretty much ignore that carbon. All right. Okay, then wrapping up here, you do want to make sure that you understand what activators, deactivators are, this ortho metapara that we talked about. One thing to also keep in mind here in terms of the safety, you don't want to wash your glassware with acetone because in this reaction you are going to be using bromine. Okay, and so whenever you have if you have any bromine left in the glassware, acetone will react with it and create a very powerful lacrimeter, and really that just means it's gonna make you cry like a baby in its crib. Okay, and then next up, phones. Here it says phones are not an acceptable source to keep time. Technically, they do allow you to keep time, right? You got a stopwatch function. Most of you have smartphones, so they do have a stopwatch type function that allows you to keep track of time, but you don't want to do that because you're going to have gloves on. you're going to have chemicals on those gloves. You have gloves with chemicals on them, you touch your phone, the chemicals are now on your phone. What are you going to do as soon as you leave the lab? You're going to go and you're going to talk on the phone like, hi Bettina, can you believe that this happened in lab? Oh no, you just poisoned yourself. So that is why we do not want phones being used in the lab. All right, with that, you should be prepared for your pre-lab. Yeah. All right, good luck.